So welcome back. Let's move on to the actual material now of the lecture. We are going to look at theory this time. It's the relational model. We are going to alternate, right? We are going to have a unit on some theory, then a more practical unit. So just that you know, if you're sick of theory after 1 week, then you can go to a practical thing. And then on the contrary, if you love math, then you wait until the next theoretical part. So this is a theoretical part. So I told you about the data shapes, right? The kind of data you can have. So the unstructured data, the sort of things you do with vectors now with ChatGPT. You have trees, graphs, cubes, tables, and we are going to focus specifically on the tables, the ones that have been known for thousands of years already on clay tablets. So what does data look like? That's the first thing we need to explain with the math. And what can we do with the data is the second thing we need to explain. So there's two parts in the math. What does it look like? And what can we do with it? Today, we are only going to focus on what does it look like, and next week, and the what can we do with it parts, that's going to be in 3 weeks after the practical parts. All right. So why tables? Well, you remember that this is because of this. Everybody understands tables. You don't need to be a computer scientist. Business people write SQL for their queries. So this is absolutely everybody not with a technical background can do that. So this is a clay tablet. It's 3,800 years old. And I really, when I look at the tablet, I think of this. I mean, this is what it does to me. I have the feeling this is almost science fiction looking at something like this, a relational table on a clay tablet. And it hasn't changed. I mean, it's still a table. So this person is Edgar Code. Now you know him. He's the one who came up with the idea of data independence. And that's the idea that we can just pick whatever we want as the physical storage. It doesn't matter. The model is the same, right? I'm repeating a lot, but if I repeat, then I'm sure you will remember. So our task now is to come up with the math that does that. How do we formalize this? And in order to do this, we will first formulate our intentions. What do we want to formalize? So on the very high level, very naively, this is what we want to formalize. So I'm going to come up with a few high-level words. So first, the table is the whole thing. You might also see it referred to as a collection, right? It's a collection of records, or a relation, that would be the mathematical term, is a relation, or a relational table, right? So these are all synonyms, they all mean the same things, and I might a bit interchangeably say table, relation, relational table, so it's all the same thing, right? Then we have the rows. That is one entry in the table, one row in your spreadsheet. There's plenty of synonyms for that. Records is a common synonym. Tuple would be the mathematical word, as we will see. It can be referred to as a document, maybe more in NoSQL, but that's also work. Theoreticians refer to also as an entity in some tables. Item is another word, and then my favorite is business objects. Like there are people who just call them business objects, especially the business people. They say we have a table of business objects. It's pretty cool, I think, as a name. But anyway, they all mean the same thing. These are rows in your table. Then you have the columns. They are called attributes, but again, some people say field, property, key. Key would be used in JSON databases, right? So this is when they would call it a key. But attribute would be the most common terminology for that. So we have PID, last, first, and country. These are attributes. These are your headers. Right? Okay. And then some of the attributes are special. For example, if you have a database of people in Switzerland, one of the columns might be the AHV number, the social security number. That column is special because it identifies the person. So if you know the value of the AHV number, then you know who it is. And we call this a primary key when we have a special column like that. The first name is not a primary key. There might be several people in Switzerland called Peter or Mark or Alice, or there's going to be multiple people. But the AHV number, it's unique. So when it uniquely identifies, we say primary key. Other people call it a row ID, a name. Some people use key. So again, there might be confusion because some people say key for the colon. Some people say key for the primary key. I'm going to pay attention. So I'm rather going to say this is an attribute. Any of these, the 4 of them are attributes. And one of the attributes, in that case, the PID, is a primary key. How do you find your primary key? We'll study in 6 or 7 weeks in what we call database design theory. I run the whole math of that for you. It's absolutely beautiful, the math. But for now, just think of the half a number that identifies a person, or the license plate that identifies a car, or at least an insurance contract. Okay, then we have the values. These are what you have in the cells, in one cell of your spreadsheet. So we'll say value, cell, characteristic, fact. You might have all kinds of words, but value is maybe the most natural one. Scalar, I actually like it mathematically to call it a scalar. The reason I like it, and we'll see that when we look at the relational algebra. Who knows about vector spaces? You told me you took some linear algebra, right? So for those of you who know about vector spaces, you know that in a vector space, there are 2 kinds of citizens. There are the vectors and there are the scalars, right? And so you can multiply a scalar with a vector, you can multiply a scalar with a scalar, you can add scalars, you can add vectors, but there's these 2 kinds of mathematical objects. And here it's a little bit the same thing when we look at tables. We see in the relational algebra, we also have a distinction between what is structured, so the tables, and the values. And so it's a little bit the same difference as between a vector and a scalar. Here we have the notion of a table and the notion of a scalar, right? But again, if it scares you, the word scalar, then just say value. It's a value, right? So all of these here, we have all of these cells here are all values, right? So this is value, this is a value, this is a value, this is a value, this is a value, and so on. Now, that's not math. Here, I'm just talking, and we need to actually find the math that does that. What do we want? So here, I'm just describing the sort of things that we want the math to do for us. One thing we want in a table is that we don't have twice the same column name. You probably tried it in some spreadsheet software. At first, it doesn't tell you anything, but when you start wanting to use some special features, it starts complaining that 2 columns have the same name. So you can't have that. We don't want 2 attributes to have the same name. In that case, customer ID twice, that's not okay. We also don't want the order of attributes to matter. Do you see the difference between the 2? I just changed the order of the attributes. Right? I had PID last first country, and then I have first last PID country. But do you see it's the same data? Who agrees it's the same data? Right, awesome. So we do not want the math to distinguish between the 2. We want the math to tell us this is the same thing. Then we might also want the order of the records not to matter, right? Who agrees this is the same data, right? So we might also want to have that. So this is the order of the attributes and of the records. Doesn't matter. And now I did two things. I shuffled the attributes and I shuffled the records. Now it's a bit tougher to see, but this is actually still the same data, right? All right, so we want the math to be able to do that. But you need to keep in mind that not everybody might agree that the order of the record doesn't matter. There are people who think, for example, let me show you this one. There are people who think that the order should matter. So there are people who are of the opinion that in a relational table, you have an order, and these are not the same because the order is different. It's a matter of technical opinion. And maybe if the math could give us some flexibility to decide if we want or not the order of records to matter, that would be nice, right? And then there are people who would like to be able to repeat records, to have several times exactly the same record, the same row. That's also optional. Some people don't want it, some other people want it, right? So it would be nice if we would have the ability to do this. As it turns out, this is called the bag semantics. Bag is just a fancy mathematics word that says you can repeat things. You can have several times the same thing. So here we have 2 Ramanujan Srinivasa, my favorite mathematician, twice. And in the bag semantics, that's fine. We are allowed. In the set semantics, that's not fine. Then it would be forbidden. And finally, we have the list semantics in which you can repeat and the order matters, right? So that I'll explain again next week again, set, bag, list. So you can see them a little bit like flavors, right? When you have ice cream, you can have the chocolate ice cream, the vanilla ice cream, the strawberry ice cream, right? It's the same with relational databases. There are people who want the set semantics of relational databases. There are people who want the bag semantics of relational databases, and there are people who want the list semantics of relational databases. Now, if the math could do that, that would be awesome, right? If the math gives us the three flavors, that would be fantastic. Here they are again, set, bag, list. Do you want a set of records, a bag of records, or a list of records? Okay. It's entirely possible for a table to be empty, right? You could create a spreadsheet and put the headers and there's no record, right? That's perfectly fine. It's also perfectly fine for a relational table to have just one record. That's also fine, right? So we are going to build the math for that. Plus, we'll want to ensure a few more things for this math to actually work. Because we say here, if I come back, set of records, bag of records, list of records, but we don't want anything. We want it to make sense in some way. And so what I'm going to show you here is broken things. I'm going to show you counterexample. It's the best way to see what it shouldn't be. And that's going to be very visual. So these are three of them that I'm going to show you broken, when domain integrity is broken, when atomic integrity is broken, and when relational integrity is broken. First, this is when the relational integrity is broken. Sorry, this is broken. Who agrees this is not a table? Right, okay, so here the relational integrity is broken. Why is it broken? Because we have missing values here, missing values here, and here an additional attribute there, and so on. So that's not a table. What actually happens, we basically have multiple records, but they don't have all the same attributes. So that first criterion, the relational integrity, says we want our records to all have the same attributes. And when they have the same attributes, we have something that looks like this. Who is with me? Right? Okay, so the same attributes, and then we have these nice columns with a value in every column. Number one. Number two is the atomic integrity. Who saw the Inception movie? You remember a dream in a dream in a dream in a dream in a dream? Here is the same thing. In order to break atomic integrity, think of a table in a table in a table in a table in a table. When you have that, then you've just broken atomic integrity. What atomic integrity tells us, the values in your table, they have to be atomic values. A string, a number, a date, and so on. You cannot put a table in the table. Right? So again, Inception. Remember Inception. Who is with me? Right? Okay, so here it's broken. And if we do have atomic integrity, then we only have atomic values. Number three. Number three is called domain integrity. What that tells us is that if you look at one column, all the values are of the same kind. For example, I put it in yellow to clarify. All of these are strings, these are names. All of these are strings, these are first names. All of them are Booleans. Boolean is a fancy term for yes, no, so true, false. So these are just true, false. And all of these are integers right here, okay? If it's possible to find for every attribute, for every column, we can find a specific kind, we'll call it a type or a domain later, and all of the values here must, in the same column, they must fulfill, they must be of the same kind. Who is with me? Okay, here it's broken. You see why it's broken? Here we have, for example, a number and true, false, but these are not of the same kind, so we broke domain integrity. And here we have numbers, and here we have text, right? So of course, if you have an LLM, you might argue the LLM is going to figure out it's a number, but no, we don't have an LLM here. So this is really just text, and an integer. So we have these three rules that I showed you here. Domain integrity, in the same column, it's the same kind of value. Atomic integrity, you can't have a table in a table in a table in a table. It's all atomic values. And relational integrity, all the records have the same attributes. When you have the three together, you are in the beautiful world of relational databases and SQL. I'm just fast forwarding there. Yes, exactly. And for context, who was in big data for engineers? None of you. So maybe, oh, some of you. Okay. And maybe you can come next semester for big data for engineers. What's cool about big data for engineers is that these three rules that I just gave you, in big data for engineers, we happily break them. So we actually have tables in tables. We have messy data that doesn't match in the same column. We have tables with holes inside, like Gruyere. No, actually not Gruyere, no, Emmental. We have basically none of these. This is called NoSQL. It was also a buzzword. People were at some point very excited about NoSQL, NoSQL, NoSQL. All right. So then, given that, I told you we need to have rows and columns. We need to be a bit flexible with a set bag list. And we also don't want the order of attributes to matter. And we would like to have also these three rules enforced. Now it's cooking. So we have the attributes, we have the values. And next week, we are going to think, okay, how do we build mathematical structures that take these and that take these? This is like when you begin cooking and you put your eggs in at some place, the chocolate and the butter and so on, the sugar at some different places. So next week, we are going to cook this and find the mathematical structures that build the table out of this. Right. So I'm going to let you go so that you can go early to the Mensa and maybe avoid the queue. Thank you very much, Marcin, for moderating. Thank you very much, Alexa, for being here with us as well. No exercise session today. It's going to be next week. I will see you next Friday at 10 a.m. in the lecture hall, of course, favorite solution, but Zoom is fine too. Thank you very much. Goodbye.